All right, we just talked about small metal particles that can cause scattering and coloration in glass. Now I want to look at some other effects that scattering can cause. And so, as we talked about before, let's say we have a piece of glass. As we've talked about before, pores, grain boundaries, things like that can cause light to scatter, right? So that's why we get something that's should be transparent go to being more opaque. And so, and this is kind of illustrated here. So we have a piece of glass. There's an air pocket, which is a pore. And so we have all this light that's incident. So everything is in phase, going in the same direction. And then as it goes from the glass to the air, there's that refraction, the bending of light from the change in speed. And because of the curvature of that pore, light will scatter in all directions, right? And so it's going all around here in this case. And so it's internally scattering based on this particle. So it can do this with a pore, but also other defects will cause that same material. So it's basically reflecting on that internal surface or change in the material. And so let's look at some of the what this can cause. So as a example of this, again with the small particles, we see that scattering of small particles is really a strong function of wavelength. And that's what I also showed when we talked about the effects of these defects in the last section. So, for example, blue light is scattered much more strongly than red light. And so this is actually what's responsible for the different colors that we see in the sky, actually. So, so we see blue skies, but then at the sunset, where we're observing essentially the sun here, it appears red because that blue light is scattered away more selectively. Right? It's easier to scatter, and so that's why we see that difference in those two. So secondary particles can cause this kind of scattering. So because of this, scattering by small particles or pores or anything like that is based on the extent of those differences between the refractive indexes of that material. So, for example, pores, if they have an N of 1, they're very potent scatterers. And so that takes something that should inherently be clear, so light just passes through it. But if we have that material as a small particle or with lots of pores and defects, something like TiO2, again, should be clear, but because of that, it becomes a very strong scatterer. And when we scatter light, that makes it white. And so that's what we're seeing with this effect here. So TiO2 is used very much in the paint industry to make things white because it scatters light, causing it to be white. Same thing, why we use for sunscreens, the non-chemical version or sometimes added to those chemical versions. We often add TiO2 or zinc oxide because they are strong scatterers of light. And so that keeps it from getting effectively to you. It can't get through that material. And so these materials become white based on that. And again, here, this is just showing you the extent of size and scattering. So we see that at this particular size, scattering occurs, for this particular wavelength, scattering is highest at this particular diameter. So the reversal is true as well, where blue light typically is more effective at scattering than other wavelengths. Okay, so based on kind of all of this, and band gap, which we talked about a little bit, I want you to take a look at these 4 materials. I've given you the band gap for each of these materials, and I want you to see if you can anticipate which one or ones will be transparent to visible light. So take a minute, look over these, and see if you can determine which ones you think will be transparent to visible light. All right, so we're back here, and again, I've given you this sort of trick here just so you, the answer is not directly on the slides here, but let's sort of talk through this. So the 2 pieces of information we have we're asking about if it's transparent to visible light, and so we can look up information about visible light. And then the other information is about the material, and we're given the band gap for each of these materials. And so what we need to think about is, how does the band gap compare to visible light? And so first of all, we can think back to that EM spectrum that I gave you. And so for visible light, the EM spectrum is about 1.3, 1.6 up to 3 EV. And so what we see is that energy, that has an energy, so therefore visible light has energy in that wavelength. So if that encounters a material and that band gap is higher than that, right? So 3, let's take that high number, so 3 EV. So that's the maximum amount of energy we can have for visible light. Well, if the band gap is higher than that, so if we look at all these, and these 2, zinc sulfide and diamond, have a band gap of larger than 3 EV, well, that means that light with 3 EV of energy can't do anything to affect that material, because there's no sort of, if you think about it from electrons, there's no way that we could promote an electron from one area to the other. So effectively, it doesn't interact with those 2 materials. So there's no absorption, right? Because if we were able to promote an electron from the valence band to the conduction band, then that could absorb light, right, and cause that to be opaque or give us some coloration, right? And so these 2 materials have band gaps larger than visible light, and therefore they're clear, because light doesn't influence those materials. It doesn't have enough energy to promote electrons. Whereas the other 2 here, 0.25, that's a very low band gap, right? So visible light has enough energy to cause absorption of the light and promote an electron. Same thing with this cadmium sulfide. It's very close, but it has lower energy than that 3, right? So this is why so just by knowing the band gap of a material, this can also tell us about whether a material will be transparent or maybe have some coloration or be dark, right? And so this kind of explains that. And so then you can kind of extrapolate that to a material that is metallic or has conduction, right? Very low band gap, and that explains why those materials would be dark, right? They absorb all of that visible light. And so for the answer here, then, if we're looking for those transparent to visible light, we're talking about diamond and we're talking about zinc sulfide.